testing of hardware, software, and manufacturing. And yeah, maybe a bit of a background information why we came up with this topic for our workshop. If you think about all the products nowadays, they can be pretty complex, and I'm not talking just about engineering products or products like computer chips, for example, but also software products. And typically they undergo not just one product stage, for example, the production, but they have a whole product life cycle attached to them. And this is indicated by these 3 boxes here, and of course it does not stay there actually. All these boxes might have even more complex sub-processes that have to be a part of the development. So it's not just the production itself, it's the development step before that, it's the service phase afterwards if the products are rolled out. And of course, testing plays a very important role in all of these phases and potentially also in the sub-phases. Why is that so important? Of course, people and especially companies would like to keep up a high quality of their products because this has direct influence on their revenue, and they would also like to understand where the problems exist as early as possible in these pipelines. Because if you go downstream, typically, when you detect a problem there, normally it's much more expensive to get it fixed than if you already realize it at one of the early stages.
For over 131 years, the University of Oklahoma has been making an impact. It is a legacy of excellence, a legacy defined by courage and determination, a legacy of champions, both on and off the field. And we're not done yet.
Just thank you. Small mishap. So visualization can be a part of this testing, obviously. As soon as it cannot be done automatically anymore, if it gets complex and human intervention or exploration and decision making is needed, then I think visualization is a good part of this testing support for all these pipelines. And this could be either in individual test stages or by connecting these different test stages through workflow support, or also by monitoring, for example, if a software product is already running and used by different users. So this for the background. Now maybe for the organizational things. We accepted altogether 5 regular, we got 5 regular submissions and accepted 4 of them. All of them went into the IEEE digital library. And so we had a proper review process where each submission was reviewed by 3 PC members, and the final decision was made by the organizers based on the reviews and discussions. And of course, we avoided conflicts of interests here. We also would like to thank our program committee. You can see the list of persons who took part in this here on the left. Maybe you can give them a brief applause because they did really a good job. Thank you very much. And then I also would like to point out that this is organized by 5 different persons. So Stefan Wagner, unfortunately, could not be here on site, but all other 4 are here. This is Catherine Isaacs and Timo Ropinski and Daniel Weiskopf, yeah, and myself. So here is the program on what you can expect for today. We first have a keynote by Matthias Sauer. He's working for Advantest. I will say a little more in a minute. It's on applying visual analytics for improved semiconductor in manufacturing and test. Then we will have 2 regular papers that are presented. After the coffee break, we will have another keynote by Daniel Fischer, followed again by 2 other papers that are going to be presented, and the workshop wrap up and closing afterwards. So before we begin, maybe just one small request. We created a little survey on the workshop website. You can access it using this link I show here on the website. maybe we get a little feedback from you on these topics. Maybe you see other domains where visualization could play an important role for testing, or you are interested in pointers to papers and other resources in this field, then please state that, or we can add you to a mailing list for exchange on a topic, for future exchange. And of course, we're also interested in general feedback. So then, we go to the first keynote. I already read the title. It's on applying visual analytics for improved semiconductor manufacturing and test. And the keynote is given by Dr. Habil Matthias Sauer. He received his PhD in habilitation on using formal methods for semiconductor test and reliability from the University of Freiburg. And now he's part of the applied research and venture team within Advantest, a leading semiconductor test equipment supplier. There he leads the European lab, innovating and venturing data-driven solutions across the entire semiconductor value chain. And I hope he is available virtually and live for that. And maybe we can switch right to him. Matthias, the stage is yours.
Does not seem to be the case.
So now it seems to work. I can hear you at least.
Ah, perfect. Okay. I can hear you as well. Can you also see my slide? Just to avoid talking and nobody can hear me.
We hear you. Can you hear us?
Yes, I can.
Okay. So then, please, Matthias, the stage is yours.
Okay, perfect. So thanks a lot for the introduction and the very kind invitation to speak on this workshop. It's about semiconductors, and it's about how we can apply visual analytics for improving semiconductor manufacturing and test. So I keep this a bit lightweight. I'm assuming that you're not too much familiar with semiconductor manufacturing, but I hope I can still convey the message why this is important and what is important also from the visual analytics side. So let me get started and get into that. So first of all, just a little bit of background. I guess we all have been exposed quite a lot to semiconductors and all the products and all the solutions that are driven nowadays by semiconductors. You have heard and seen such kind of motivational slides, I guess, over and over again. So I won't go too much into details here. What I still, on a personal level, what I found quite amazing is in the last kind of, let's say, 5 years, maybe a little more, a bit less, a complete new class of applications that are driven by semiconductors came up. And this is this whole class of having sensors, having measurements right on devices. So semiconductors are not only there to kind of compute like a processor, but really can interact with the world around them. You have sensing, and this really creates this interaction on quite a new level. So you see this whenever you think about autonomous driving, when you think about novel trends like augmented reality, if you think about even Meta, that changed the whole company name to go toward that direction. So that's really a new world that's coming up. And of course, there's much more ahead of us. But I would like to take the whole story maybe from a different perspective, from a different angle. And this is kind of what you see here, what I try to illustrate on this slide, which is simply on the left side, a picture of the transistor count over time. You can argue a lot whether it's still Moore's law, named after the founder, one of the founders of Intel, is still valid, meaning we still have a doubling of the number of transistors, so the basic building block of a microprocessor of a chip, if that still is doubling every 2 years. But what you, without any arguments, can say is you have a great increase in transistor count. So when the first integrated circuits came up, the first products came up more like in the 70s, you had an order of a few thousand transistors. Nowadays, you're easily in the billions, say tens or 15s of billions of transistors. And for me, this is really amazing that in this 50 years, that it had been able to scale technology, density, power levels, but also the tooling and the software around this so massively that we are able to put semiconductors on this kind of huge scale. And while Moore's law is quite, simple in this sense that it just says you have more and more basic computing elements on the same space, if you translate this kind of into possibilities, then you end up with something on the right side, namely saying what would actually happen if you compare the technology from a few years ago to nowadays. And if you simply do a bit of math, then you would end up with like around about 200 million of cost for a simple microprocessor. Nowadays, if you would produce this with the technology of the 1970s. And for me, that's quite amazing in terms of it's not only transistor count, it's not only capabilities, but it's more like if you think about the pricing, if you think about the street price, a very expensive microprocessor is in the hundreds of dollars, but simple ones or graphic cards or so, you get them in the market for tens or 20s of dollars. And if you see all the computational power and everything, that's really a fraction of what it used to be, and it's really, really powerful. And quite some technology has been evolving around that to make it happen. And this kind of drives all the applications we have behind semiconductors. But if you think one step back towards what I just told you on the previous slide, all this kind of technology scaling, all this kind of complexity behind the production. Semiconductors production is a really, really complex manufacturing process. It's on the edge of the technology limits. You are writing or creating structures in the low nanometer sizing and billions of that. So if you just think about that, creating billions of elements in nanometer sizes, then it's quite clear that you are not able to produce each and every device in a way that is working perfectly. That's, as a matter of fact, not possible. So it's all yield-driven, which essentially means you have to test it. Each and every semiconductor needs to be tested fully for functionality, and especially depending on its use case. So if you are within an airplane, a car, for instance, then you need to test your semiconductor in much more details. And this is really a major driver also of cost. So if you think about total manufacturing cost for some devices, you can reach 25% of the total manufacturing cost is associated to testing. That's mostly due to the fact that during production, you can produce whole wafers. So you can produce like hundreds of devices at the same time. But for testing, you need to test each and every chip, each and every device independently on its own. And therefore, this is quite some effort. But still, it's unavoidable as there are a lot of defects, a lot of issues that can happen during manufacturing. Just a few examples of this, going to be brief. You can spend ages discussing this. There are actually two kind of main classes of manufacturing issues that can happen. On the one hand, there are the defects, which are due to manufacturing processes. As said, you are trying to create structures in the low nanometer sizes, and therefore all kind of hiccups can happen. Like what's quite easy to understand is if you think about two metal lines close to each other, that you can have some unwanted connection between those lines, like a bridge, or you can have an open, like displayed here, so a wire connection in the circuit that is not connected properly. Such kind of imperfections can happen easily, and it's the job of test to find out what's really happening. On the other hand, there's something like process variations, which are a bit more subtle. This is more like we are talking about Gaussian processes, we are talking about manufacturing, where you cannot achieve a 100% identical product. So there's always a bit of a variation, and depending on how the specific process, how the specific device ends up on the distribution, it can be a bit faster, a bit slower, and so on. So this is quite subtle to find out, but also this is the job of test. So for instance, if you buy a processor from like Intel or AMD, you get a speed crate, and depending on the variations of this device, the vendor is selling that for like 2 gigahertz or 2.2 or whatever kind of speed crate. So this is happening, and essentially the process of semiconductor testing, in a nutshell, it's quite simple. You produce input signals, you apply that using machinery, complex machinery, a tester, to the device, to the chip, and then you check at the end of the day whether the response of the device is as expected. If it is, the device is pass, otherwise it's fail. So from this perspective, semiconductor test, if you really boil this down to the essence, is not really different from other kind of testing. Input signals, checking if the result is expected, and pass-fail. Obviously, there's a lot of challenges in terms of selecting the right input signals, computing that, namely to identify whether these input signals really have a meaning on the output. There's a lot of technology challenges, how to design the tester, how to keep the signal integrity, how to keep this everything dense from the electrical and the spatial components, and so on. But for today, I will not go into details here, because what I would like to tackle on in the remaining part of this talk is visualizations. And as you can imagine, for visualizations, for semiconductor test, there's actually quite a lot of data that is generated. So in terms of capturing the results of the devices, capturing the feedback of the devices, and these kind of data capturing analytics, this is really important and crucial in order to determine the success of a product. Because at the end of the day, what's happening is, if you think about all the complexities I mentioned earlier on when producing a product or designing a product, typically what's happening is this is really a yield-driven process. So when you start with a few prototypes, when you start your early production, actually just a few percentage of the chips are working. It depends from product to product, depends on whether you have a new process or not. But for like new processes, for really top-notch devices, you can think about start production and just have like 20% of yield. So which turns into 80% of what you produce is actually thrown away. Now, that's not a good and a viable situation. As engineers, you need to work hard and look at the measurements, at the data, to improve here, tune the production processes, understand any kind of imperfections on the design, on the process, and where to tweak that. So the essence of it is really, after starting production, there's a yield learning phase, a yield ramp phase, and to keep this phase as short as possible, this is one of the key success factor for a company. So some companies are better in this than others, and this is to a good extent that this is determining the success, the economical success in the market. So therefore, it's all about producing, designing the right products, but also learning from the production, learning from the data, and understand what's happening. And in this understanding, at the end of the day, engineers play the major role to be here in such kind of improvement cycle. So you take measurements of the devices or part of production, you get data, and then it's key on visualizations to tell the engineers what's actually happening to guide their understanding so decisions can be made in order to change or improve processes. And this is turning over and over again. So one of the specialities here is really you deal with engineers, you deal with human decision making, and that needs to be assisted and supported as much as possible. And one of the classical examples here in terms of what kind of visualizations in semiconductor we have quite often, these are like classical true plots. Just one of the examples, you see them over and over again. From a visualization point of view, this is just kind of a 2D plot. You get the parameters, you're varying, like classically frequency and supply voltage, and it gives you kind of the working area here in green, and this captures essentially with one view into that. As an engineer, you can say, okay, this is my working area, this is my working function, and in this range, I can operate myself. Very classical, very simple, regardless where it's a 2D variant or sometimes you have a 3D variant, but classically it's 2D. But of course, this kind of SHMU plots have one major issue here. And this is kind of, there is always this challenge of, on the one hand, you need more data. So when you look at your production, when you look at the device, when you try to understand what's happening, you really need to measure a lot. You need to get an understanding here. And one of the issues of SHMU plots, especially if they are like two-dimensional, is, well, you keep two parameters, you variate them, but there's a high danger that you end up in areas that are not really the core of your problem. So especially since you're limited in the number of dimensions you can look into, like 2D, 3D, there's a high chance that you miss complex correlations. At this point, I like a lot here this picture of this elephant. Maybe you already have seen that. But if you think about a few blind people looking at the elephant, trying to grab how it looks like, and depending where they touch it, depending where they look like, they have a different imagination of what they see in front of them. And the same we have experienced also with engineers. If they look at some data of semiconductor, if it's too narrow, just looking at a certain perspective, then you have a high chance of missing the essence. Just like in the elephant, you think about the wrong picture. On the other hand, there is also too much data. Meaning, typically, if you measure the behavior of a semiconductor, you can have hundreds or thousands of measurements. And you cannot have variations in plots across all of them. So this would end up in a combination of thousands of plots. And as a human, well, it's really hard to grab anything. So especially if it's like two-dimensional or you even need more complex behavior. So this is a classical situation, a classical challenge we see, probably not only in semiconductors, but that's probably true in a whole lot for technical domains. Yet they need to find a solution in terms of what you're looking for and where the essence of the data is. And this is where kind of data analytics platforms that also contain visual elements come into play. So you store all this kind of data and you look at them from a statistical point of view, but also from a data correlation point of view. So this is exploiting the fact, when you look about semiconductor production, one of the advantages here, so especially when you're in high volume manufacturing, is you're not only having 1 or 2 devices, you have millions. You generate millions of devices, and this means you have a whole lot of data. Each device is coming from a certain lot, from a certain wafer. You have XY coordinates. You have a lot of measurements. And in the first place, you drive this analytics from a statistical perspective, from a visual perspective. You load the data, the production data, in some kind of data analytics software. This is nowadays standard. Different vendors have different kind of software and platforms. But at the end of the day, it's a huge database where all these millions of data points come into. Each device, full traceability in terms of devices have their names, their IDs, and you can associate the measurements and identify drifts over time. So this is really like a statistical analysis. You look into the distributions, you look into changes in the distributions from one parameter to the next, and you also drive in a process way to drive your processes from the point of standardized statistical metrics like CPK analysis, like a 3 sigma outlier analysis. So you always come from a statistical point of view and you try to assess whether things are normal, whatever normal means, so within your previously defined statistical ranges, or whether things are outside. And this helps a lot to identify correlations, to identify outliers, in generally speaking, to identify tests that fail more often than expected, and act then as a first point for the engineers to look deeper into that and see whether process parameters or test limits or anything needs to be adjusted. And as part of that, what you typically also have is, as a very classical visualization technique, is wafer maps. As the wafers are one of the basic elements of semiconductor production, so you're producing in this circular fashion. On one wafer, you have like hundreds to 1,000 semiconductors, ICs at the same time. You produce them at the same time in the production, the same machinery. So therefore, defects on the wafer has a whole lot of correlation to each other. Depending on its underlying root cause, these effects can be more like random, can be more like oriented on a certain space, can have a parametric distribution, like from being devices are faster from the inside to the outside or so. And therefore, one of the specific visualizations that we find in semiconductors is the wafer map. So you show a certain parameter over the XY coordinates, and from there, give it to the human to show, and he can make a whole lot of reasoning on the underlying issue. As an example, which is quite obvious, often, especially in the older days, you see things like scratches. So really kind of a metal or something that scratches the wafer. Sorry for that. I'm sorry. So you see like a metal that scratches the wafer or so, something that's left over from production. And this is still kind of visible then also in the wafer maps. Nowadays, what you even find more and more is AI that helps a lot in the data analytics. So traditionally, it was about humans. It was about showing graphs, showing visualizations to a human. Now, what we see more and more as trend is AI support assistance here that takes the data and supports the human in pointing into the right direction. So just as one of the examples here for the scratch, the AI would highlight that and kind of here this random noise that is always part of it would be blurred away so the engineer can focus on what's actually happening. And this is a general theme that we see, that in the semiconductor area, we have a whole lot of data, and there's a need for research on how to support and how to help the engineers in their data analytics. So before closing, let me quickly point to one of the activities we have from Advantas together with the University of Stuttgart, that is namely a full graduate school called Intelligent Methods for Semiconductor Test and Reliability. I see Andres is also one of the speakers here. He's also part of the graduate school. We founded that graduate school to work together with the University of Stuttgart on research questions, on methodologies that help engineers in getting more and more effective in their data analytics and in understanding root causes better. So overall, they get to faster reasoning, and thereby we hope and are confident to improve semiconductor manufacturing and production in the future. Having this said, let me conclude my talk. So first of all, you know quite a lot that semiconductors are one of the essences that power all our digital world. Still, its production is really, really complex, and it's a yield-driven process. So therefore, test is a very essential step and is really essential for keeping and maintaining product quality. There's a lot of data that is generated by semiconductor test, and visualizations help the engineers to understand root causes and drive corrective actions. As an outlook, more and more AI-assisted analytics and visualizations come up to support the human. That's it from my side. Hope I could give you a bit of a glimpse into semiconductor testing and the data behind that. And of course, if there are any questions, I'm more than happy to reply to that, to answer that. For now, thanks a lot for your attention.
Thank you very much, Matthias. Very interesting talk. Are there already any questions? As far as I saw, there are none on Slido yet. Please remember, you can ask questions on Slido, but of course, you're also free to use the microphone to answer them. Maybe if you don't have, there is one.
Hi, I'm Philip. Thanks again for the nice talk. So one question, after applying all these visualizations and data mining the issues in the earlier stage, do you have any numbers on what kind of impact this has compared to the time before you didn't apply these sort of visualizations to find the errors? So could you measure any benefit resulting out of that?
Yes. So at the end of the day, this is the whole reason behind these actions, namely to improve yield. So this more or less comes down to this yield curve I've shown in the beginning. The effect that this yield curve is raising, this is not like kind of single step. These are more like hundreds of improvements you do one over the time. And so it's a result of many, many small steps. And these are kind of associated with the changes. And the companies also, we do very detailed tracking in terms of which change leads to what improvement. So in the data, in the statistics and everything, there's a deep analysis to say, okay, if I now change, for instance, this limit or change this this issue, this design, then I get 0.5% yield or so.
I see. Okay, thank you.
You're welcome.
So any more questions from the audience? So if not, maybe I have another one. Matthias, could you comment on how well integrated those analysis tools are so far? Are they more like individual solutions for individual problems? And maybe as a follow-up question, if they are not completely integrated, would that be something that is to be pursued?
That's a wonderful question. And I would say this is one of the major activities and changes in semiconductor test right now. Namely, the integration of this data analytics platforms with the measurements. This is something that is now coming up, and there are different vendors like ourselves, Advantest, but other companies are working towards this goal to create one big data universe where everything is located, kind of from design to test and the different stages. In the past, this did not happen, mostly due to the fact that semiconductor production is quite complex. There are many, many companies involved, many different parties generate data, and the technology platforms were not ready. So therefore, there had been a lot of obstacles in the past, but now this goes more and more towards the direction of integrated data platforms.
Thank you very much. Any more questions? Then maybe one very brief final one. You talked already about the production part and how important visualization or visual analytics in general would be for this stage, so to say. Is there also interest in, let's say, when those chips are in place, in smartphones, in airplanes, wherever, to do monitoring and also use visualization for that?
Yes, definitely. Meaning, especially when it comes to in-field usage, think about a chip in a car or, as I said, an airplane. Modern devices have a lot of sensory inside, meaning they can sense itself health, like temperature, like device-specific properties. And this data is already collected and monitored on the chip itself. Now, one of the challenges coming up is how do you get that now out of the car into this platforms, this data analytics platforms I just spoke about. That's one of the challenges, but also here, this is more and more coming and important to assess kind of changes in the behavior of a chip over the lifetime.
Thank you very much for this answer. If there are no further questions, let's thank Matthias again. It was great that we had you here.
You're welcome.
And with this, I hand over to Kate, who will be introducing the next speaker.
All right, so before the break, we have two great paper talks. The first one is by Jonas Madsen, who I believe is also online. So this will be about rheological tests results from soft materials. So please go ahead and start the presentation.
And I'm Les Sol, and we are both with the Department of Computer Science at Aarhus University. Welcome to our presentation on the visual exploration of rheological test results from soft materials.
This work is a joint research project with our colleagues at Aarhus University. And first up, we're going to be talking about what is soft materials and why we want to test it. Soft materials are used in a wide range of uses. In one end, they're used as packaging material to cushion items under transport. In the other end, they're used as lubricants for gears or in machinery to make sure things run more smoothly. This is why it's important to understand and study them. And we study them by the use of rheology, which is the study of deformation, or at least one way of studying it. And what we're doing is we're looking at the viscoelastic properties of a material. And this means that the elastic property is more akin to solid, so it would be a steak. And then we have the viscous property, which is more akin to a liquid and what you would look at in water. And then we have the viscoelastic properties, which is most food items, and this is the pudding, a sort of mix between the two. And of course, it's very important to know the viscoelastic properties of materials so we can make sure that the toothpaste can be squeezed out of a tube that we use when we brush our teeth, but also that the food in our food processing plants remain food or remain solid as they get pushed through the pipes and so on. This testing has been propelled into a scientific field of its own kind by the development of more rheometers, which is the equipment used to test this study of deformation, so rheology. And the problem is that existing tools have not been able to keep up with this development. So they are severely lacking in several departments. Currently, the scientist must be analyze one experiment at a time, and then they'll have to painfully cut out the picture from the existing software, and then paste it into their own figure, PowerPoint, or whatever. They got to draw their own lines, and then insert this copy-pasted, cut-out picture into these matrix to be able to properly analyze the sample, which of course gives us a big room for improvements. Rheometers explore the viscoelastic properties of material through oscillatory test measures. What this means is there's a bottom plate, a sample, and then an upper plate sandwiched in between, the sample is sandwiched in between the two plates. And the upper plate starts rotating. And as it does that, the sample is applied stress, and it then experiences strain in response to the stress. And we do it over time, which is strain rate. And these variables are how we study deformation of materials. Most experiments, what we do is we are setting the strain, and then the stress is applied by the machine until it reaches this set strain. And this is also done in what we call amplitude sweeps. The amplitude is just the percentage of strain that you want the material to reach. And then in a sweep, you set a range of these percentages, and the machine goes through them one by one. And this is one experiment. So this is how the rheometer works.
Generally speaking, there are two main procedures when it comes to oscillatory shear experiments, and these are large and small amplitude oscillatory shear, respectively denoted as layers and sayers. They're defined by the range of strain values being swept during the experimental process. So sayers essentially investigates a material's response to small vibrations, whereas layers looks into processes that disrupt the structure of a material. The response of the materials as stress is applied can be defined as linear or nonlinear, where a linear response is when the deformation is proportional to the oscillatory stimulus, as can be seen on the elliptical shape depicted in Figure 2. Here we see that as the strain increases, so does the stress. A nonlinear response, on the other hand, results in a more disorganized response to the rotational shear, as can be seen on the right part of Figure 2. However, following a material's response when it is nonlinear is important. A representation of the stress and strain values in the time domain as functions of sine and cosine can be derived from the raw data through Fourier transformation. This data can then be visualized using Lissy curves. The standard visualization method of the data is Lissy curves. Lissy curves visualize stress, strain, and strain rate as closed trajectories in a 3D space. However, 2D projections of the space are typically used to show and analyze the viscous or elastic properties of a material. Examples of the 3D and 2D visualizations can be seen to my right. Multiple Lissy curves in combination can be used to analyze the dynamics of materials. There are two ways of conducting this analysis, which we have defined as within and across sample analysis. Within sample analysis looks at data generated using the set strain amplitudes from the amplitude sweep, whereas across sample analysis study the same material under the same strain but different conditions. These analysis methods can be used when looking at the two visualization methods known as layover plots and Pipkin diagrams. A layover plot superimposes an ensemble of Lissy curves in a single view. This gives a good overview of scale and changes in response as stress is increased. This can also be seen in the layover plot to the right, which showcases the difference in scale and shape between the different strain amplitudes of an experiment. The Pipkin diagram, on the other hand, displays the ensembles as small multiples in a matrix format. The scales of the curves are normalized so they all appear to have the same size. This helps gives an idea of the changes in response as the parameters changes. However, the sense of scale is lost. This is clearly shown in the diagram on the right, where all curves appear to have the same size.
Shown on the current slide is an image of the VAS software. This is the solution that we developed to try to fix some of the existing problems. On the left side, we see the data loading and parameter settings, which, as the name says, is where you load your data, and also you can tweak the data if you want it to be loaded in a different way, but you can also change the parameters of the data set itself. And here in the middle or right side of the screen, we have the visualizations in a dashboard setup. And at the top of the screen here, we have the tabs, which is where you see the graphs, all the available graph types individually. And you can do this before you add them to the actual dashboard itself by pressing on the buttons down here in the right corner. This is where you find the buttons to remove or rearrange or add graphs to the dashboard, but also where you find the existing predefined arrangements of visualizations, also called the templates. The design process was supported by domain experts from the Department of Food Science at Aarhus University in Denmark. They assisted in understanding the domain, the research field, equipment, and currently used software, which also helped us to arrive at these 4 design requirements. So the first one is interactivity. To be able to perform data analysis within sample and across sample directly in the software instead of having to rely on manually arranging them in some other place. Existing tools in the field were very lacking in this interactive exploration. The next one is the flexibility to configure the UI so that it is in line with the data analysis task at hand, instead of being confined to ill-fitting standard UI. The next one was scalability, to be able to cope with datasets spanning multiple rheological tests within sample and across sample, instead of the user having to manually split these datasets so they can analyze them individually, because that's what the existing software needed. It was also unable to handle larger experiments as it was taking too long to load them, performance-wise. The last one was the ease of use. In having a self-contained software instead of packages to be run inside another environment, which in some cases had additional license fees, and there were no real export capabilities outside of relying on screenshots. So these 4 were the big main points of our new design. And as we implemented the features, the expert also commented on the early prototypes so that we had this iterative design process. The design requirements mentioned earlier were mostly all of them solved by the use of a dashboard design. So what it allowed to do was the user could freely add views, remove them, or rearrange them on the dashboard, with each view containing a visualization. This allowed them to customize the board to a specific task at hand. They could also save these setups, customized setup, as templates, so for later usage, they could load them up again and reuse them. The user could also do brushing and linking across the views because of the dashboard design, which helped the user focus on a specific data point when doing these visualizations, or to help them discover new features of the dataset, or just focusing when doing a specific task. This is the brushing and linking in action demo. So here I can select a specific sample of the experiment and see it highlighted elsewhere in the visualization where it makes sense. The data importing was also a vast improvement, offering the ability to import multiple experiments in one go. It also features the ability to preview the data before importing it into the software, and allows the user to include or exclude specific amplitudes from each experiment or specific experiment. The machine parameters are automatically loaded in if included in the file name, instead of having to manually type them in every time. The export functionalities are likewise improved. The user can tweak the visualization as they want for export, from actual visualization tweaks to just purely visual tweaks for publication purposes. We have also improved on existing graph types in the field. One example of this is the Pipkin diagram. So as we can see on the slide, we see a matrix graph of these Lissajous curves. And behind the Lissajous curves, every row has a line graph. And this is a max stress line graph, showing the difference in stress levels across as the strain amplitude increases. And there's also a number above the Lissajous curves. This is a quantitative measure that tells you more information about the viscoelastic properties of material. One example of this is what we call the strain stiffening property. And this helps the user gain more information from a simple visualization instead of having to manually compute these properties or having to look at other visualizations to gain the same information.
The visualization of data using VS is optimized for up to 5 symbols. These are stored in 5 separate Excel files consisting of 5 sheets each. You can see the sheet structure at the bottom left of the Excel sheet. Each sheet contains the values of measurements during a certain strain threshold chosen during the experiment. Looking at the computational scalability of the software, the Fourier transform starts becoming noticeably long, which can hinder analysis when the experimental data consists of around 15,000 measurement points. This is, however, not a critical limitation, as most rheological time series are much shorter. At some point, the structure of the material is broken, and it just makes no sense to continue the experiment. VS has primarily been evaluated through a use case scenario and 2 expert interviews. The use case scenario explored test data which was extracted from 3 different mozzarella samples sampled at different processing stages. 2 of these mozzarella samples can be seen here on the right. Looking into these materials' response at different processing stages can help give a better control of the process and ultimately lead to a more consistent quality. VS has the possibility of generating a heat map depicting the contribution of each harmonic in the Fourier transform. This assists the user in setting the optimal parameters for the analysis. This heat map clearly shows that the relevant contributions to the result are made by the first and third harmonic. These can then be chosen for the processing of the data before visualization. After processing of the data, the visualizations are loaded into the dashboard. The similarity tab of the dashboard gives a comprehensive overview of the 3 samples. It helps show that the characteristics of the materials change with increasing strain amplitude. See error 1 and 2 at the Pipkin diagram. The materials M2 and M3 that have a similar response in the Pipkin diagram as the strain amplitude is increased can also clearly be singled out in the similarity map and matrix. The main takeaway from the 2 expert interviews were that first, visualization in general and VS in particular can help with a qualitative understanding of a material. Secondly, using these visualizations allows for more accessibility to the field, as understanding these visualizations might require less mathematical background. Thirdly, the usage of the linking and brushing by the experts was very limited. This might be due to the fact that visualizations within food and material science has typically focused on presentation rather than exploration. Another reason might be that in current software, the visualizations are isolated and not shown in combination. The last takeaway is that layers rheology is not yet the preferred rheological analysis method. And this also means that as layers is still an evolving field, VS must follow the evolution of the field in order to actually stay relevant.
So we have now presented the software tool VS, which enables visual exploration of rheological test results. State-of-the-art was advanced in 2 important aspects. First, was researchers are provided with free software that incorporates the analysis and diagramming features in an interactive one-stop solution. And the second one was that the modern visualization research and techniques are introduced to the rheology field, which has not been benefited from this over the past 30 years. There's not been any development in the area. And we have now introduced a small part of it, but a beginning and a scalable software that can include a lot more. Package of VS is a usable software tool in its existing state, but because of its scalability property, as the years go on and more visualization research is done within the field, it can all be incorporated back into VS, and therefore it should remain an all-in-one solution.
Thank you for listening. If you have any questions, feel free to ask them after this presentation.
More information about the project and a place where you can download the software itself and its source code can be found at the website currently shown on the slide, which is vislineau.github.io/VS. Thank you for listening. Hello, my name is Jonas.
All right, now. Oh, and it's so good to have you guys online. So I don't yet see any questions in the Slido, but if those of you in the audience, you can also raise your hand. I also like to say this is lovely work, and I highly recommend you go to that website that was on their final slide, and I will also put it in the Discord later. It has some really nice demo videos there. One of the things that I found really interesting in the paper is you note very early on the importance of flexibility in testing. But then, and so you built this beautiful brush link system, but then the people who were using it were not ready for that. However, you had a lot of nice flexibility in the data import, and I was wondering if you could talk a little bit more about how your interview participants used those to set what they were going to see when they imported the data.
As you mentioned yourself, the flexibility in the import feature was also quite new to them. Luckily, it was quite early in the process that we made it, so we were able to pretty much guide them a lot into using it more. But we noticed that it was unusual for them to use it, so we tried to really get really deep into the process and how we made this. We didn't show a picture of it, but we really focused on making it as user-friendly as possible to really entice them into using this new feature. In the brushing and linking feature, it's less noticeable that you can press things and so on, which was areas that we could have worked more on. But in the data importing, it's really obvious that you have to use it and try and press things to really get the maximum out of it, if that answers the question. Maybe Last has something to add on.
Yes, thank you. And we have another question from Slido, who also points out this is a fascinating application of Viz. So Cameron Yick asks, how long does it take people to learn or notice useful patterns in these Lissajous, layover, and Pipkin diagrams? So, like, what were people using to produce these graphics before as well?
Beforehand, they used MIT layers typically, or other packages, for example, the MATLAB. And here they create these singular graphs, which they then have to crop, which takes a lot of time because they had to go through each strain percentage of each experiment individually and create these graphs. Whereas with our import system, they only have to choose 5 Excel files, and they can do this simultaneously.
All right, thank you. So let's thank our speakers again. Thanks so much for your work.
Thank you. Thanks for having us.
Yeah.
All right, our next talk will be on interactive analysis of post-silicon validation by, I believe, Andres Lalama. And is this pre-recorded as well? Because, all right, so let's get going.
Hello and welcome to our talk, Interactive Analysis of Post-Silicon Validation Data. This work was done as part of the graduate school Intelligent Methods for Testing Reliability. That is a cooperation between the University of Stuttgart with Advantest, a leading semiconductor test equipment provider. This work was performed by myself, Andres Lalama, together with Johannes Knittel, Steffen Koch, Daniel Weisskopf, and Thomas Ertel of the University of Stuttgart, as well as with Sarah Rodacker, Rafael Lati, and Johan Riva of Advantest Europe. So, let us start. Let us begin by explaining what is post-silicon validation. Post-silicon validation is a step in the chain of chip production that is performed after the first real prototypes are generated. That means after real physical chips are generated, some special tests will be run upon those, and post-silicon validation must ensure that the fabricated chips and the firmware meet all of the specifications without problems, under all operating conditions and modes. Now, let's define what type of problems we find when doing post-silicon validation. As discussed with our experts, problems in post-silicon validation debugging, they cannot always be directly pinpointed, but rather they present symptoms which might and might not be an indicator of failure. So what exactly does this mean? It means that they do find problems. Sometimes these problems present the same type of behavior, which we call symptoms. And the main thing we want to achieve right now is to identify and separate those types of problems. And we of course also want to explain those problems in terms of their input value ranges. The constraints we have is that they should be plausible as well as interactive. So that's the main thing we wanted to do, was to generate some interactive analysis workflows. And this should also be really easy and comprehensible for people which are not really in tune with ML projects. Let us have a look at the data. The data consists of mainly three attributes. System attributes, which are composed of data like test case number or test equipment used. Input attributes, which can be raw or computed, such as voltage and current. And lastly, output attributes, which can also be raw or computed, but important for us is that these outputs can also be seen as symptom attributes. If you remember, as I said before, we will want to separate problems depending on these symptom attributes. And we can also here define target attributes, which will then tell us if the outcome of a test is positive, neutral, or negative. In order to solve this problem, we developed an interactive analysis workflow that consists of 4 stages: data selection, candidate identification, problem refinement, and problem analysis. Users are central in this workflow and can go back and forth between stages as needed. In order to try out the workflow, we developed a web application. All of the images and videos you will see in the following slides are being performed on that web application. First stage, data selection. The user starts by loading a dataset into the application. After that, the user has the option to load a second file containing expert knowledge, which classifies attributes in the categories discussed before: system, input, and output, as well as describing which outputs can be considered symptoms. If you remember, we want to assess problems depending on their symptoms and separate them. After the files are loaded, the application will show the attributes in a tabular way and give some insight upon the entered data. The view is composed of a file selection component and the attribute table component. Now let us highlight some of the automatic preprocessing done after loading a dataset. The application will recognize and disable attributes, for example, if there is no variance in the attribute, or if the attribute is completely empty, as well as if it recognizes the attribute as being only a counter. It can also handle missing data by dropping the data items, or by filling them with a user-defined value, as well as just taking the mean value of the attribute. It will also display the data distribution of an attribute as a histogram, and it will automatically switch and select between the linear and logarithmic scales. Of course, the user can also switch between those scales. Last but not least, we also allow here the selection of the target attribute. Second stage, candidate identification. This view is composed of mainly 3 components: the projection component, the clustering component, and the parallel coordinates plot component. How to visualize multidimensional data into a 2D diagram? Well, the answer is dimensionality reduction. As you can see in this image, we are using UMAP to visualize the multidimensional data into a 2D scatter plot. In our case, we are only using the system attributes because we want to understand already if they have some similar behaviors when being projected into 2D. What will be, of course, the next question is what will happen if we add some type of coloring or some clustering into this assessment? After the data has been projected, we can further enhance the view by defining ranges based on a chosen target attribute, here the total. The user can define value ranges for positive and negative data items, with everything in between being set as neutral. After the user has done so, These ranges will get mapped as color into the projected data. The user can then directly observe some of the positive and negative clusters which has been built with the data. Computed clusters. Since the projection might not always succeed in separating groups of problematic cases and presenting them as visually distinguishable clusters, the system also supports the computation of clusters in the multidimensional space by applying k-means clustering, either using only symptoms or only inputs. In our case here, we are using the inputs. Why? Because we want to see if the symptom attribute, which we projected in the step before, using UMAP, correlate to the clusters which have just been computed with the input attributes. What we can see here is that they are similar but not really completely overlap upon each other. The calculated clusters, which are depicted right now with the colors, are larger than the clusters which we found. Cluster selection for further analysis. The user can select a group of data points that show similar behavior, give them a name, and save them for further refinement. Here, we want to select negative outcome data items as well as ones containing mostly positive outcomes. Why? Because we want to later determine how they differ from each other. We want to compare the really bad ones to the really good ones. And now that the user has identified some clusters of interests that they want to better understand, we continue to the third stage, the problem refinement. We present a view that allows investigating and modifying those clusters of interest. We have to remember a failed test case may have several reasons why it failed. We visualize them in a row-based layout for easier comparison. Each row represents a possible problem, and in order to further refine the clusters, we reproject the clusters of interest only upon the date of the selection. With this, we compare the global to the local projections and can find different structures. To better analyze the selected clusters individually, we need a source for comparison, which is the reference cluster. The reference cluster can be all of the data, one cluster, or a union of clusters. Remember, we want to compare against clusters containing mostly positive outcomes and see how the clusters of interest behave in comparison to the reference one. After selecting a reference cluster, the application will generate a scoring based on the Kolmogorov-Smirnov test. This test shows us how similar two distributions are between each other, in our case, the histograms. That will give us a sense of which attributes are the most significant for a given cluster. Cluster significance assessment. Let's take a closer view on how this works. Here you can see two different candidate problems. First, we can remember the selection made upon the regional global projections. On the right of that, we see the local projection of each of the clusters, in this case not having any new information. After that, we see the KS test scoring of the different symptom variables. Let's take a closer look by selecting the frequency error. When we select an attribute, the histogram will display the data of that attribute on the different histograms. The scoring was calculated by comparing the top histogram, here blue, that represents the frequency error distribution inside of the reference cluster, and the bottom histogram, in this case red, that represents the distribution of the frequency error for each candidate cluster. First, we notice that both clusters differ from the reference clusters, which is already good. Interesting is here that both of these clusters represent a negative net outcome, but they also differ on their distribution. This is a good indicator that the two candidate problems might refer to different problems. After the user finds some of these different attributes, which are really significant, the user can then save them into a structure and go to the next step of the workflow. This leads to the fourth and final step, problem analysis. In the problem analysis view, we first have a list of the previous selections. These selections are represented by the symptom variables saved together, which we did in the step before. Here, we use the selection as a new Boolean attribute and add this as an extra information to the dataset, in this form. So, with that changed data, we can now run the mutual information algorithm and get a score that depicts the dependency between the attributes or set of attributes to a given target variable. This can be 1, 2, or 3 input variables and the chosen target. The results get displayed as nodes that are ordered depending on the score, as well as the number of input variables which are part of the set. If the user selects a node, this will populate the selected node component and show the significant symptoms that contributed to the selection, the input variables calculated by the mutual information algorithm, and also will populate the parallel coordinates plot to get a better grasp of the dependencies. With that, we have finished the last stage of the interactive analysis workflow. Use case. We describe the following use case based on a proprietary artificial benchmark dataset, which is based on realistic scenarios and was created by domain experts. We assume here that we have a clocking chip that should not exhibit too high jitter. That is, the timing of the output signal should not deviate too much from the ideal values. The dataset consists of 10,000 data items and 64 attributes. We had the support of the domain experts with whom we iterated over several versions of the workflow. Regarding the results, we showed a lot of the steps we took upon the use case in the slides before. You saw we chose one candidate problem with the following meaningful symptoms: a random, that is random jitter, as well as limits of control deviation, dt-min and dt-max. With that selection, we ran the mutual information algorithm, and then in selecting the node that represented the sets of input attributes, P, FCKD, and T-imbal. That node had both the highest score and also consisted of the highest amount of attributes. P, that is a general output divided factor. FCKD is the frequency of the signal CKD. T-imbal is a time intervals imbalance quantifier. What it was most interesting for us is what we found when we looked at the parallel coordinates plot. That is, that all of the negative cases go to the same value of P, 1.5. That is consistent with the ground truth of the problem asymmetric output which we're looking for. Summary. In conclusion, we have generated a comprehensive, controllable visual analytics workflow for post-silicon validation. This workflow supports validation engineers in separating problems, as well as helping validation engineers to explore the causes of individual problems. We leverage steerable interactive machine learning methods together with user-friendly visual representations. That helped us to deliver a gentle learning curve that will help newcomers to promptly start analyzing problems. Future work. We want to enhance the problem analysis view to better tackle the tasks faced by the engineers. We feel that scoring nodes right now feel kind of clunky. We first need a strategy to optimize the time to run the algorithm, since we have a factorial growth of the combinations. Right now, we just run less combinations than we would like to because of the runtime. We want to understand when does a single attribute get substantial information when paired together with another or several other attributes. We as well want to use a hypothesis to generate more tests and to test those results. So what we generate right now on the last view is a hypothesis. So we would like to have a way of generating new tests and test this on the fly. Last, we want to bundle all of the workflow steps into an all-in-one approach. As happy as we are with the stages of our workflow, we feel the need to want to reduce the amount of views needed to go through the whole process. So this is also a current work which we are doing right now. So, thank you for listening to our presentation, and I will be happy to answer any questions. Oh wait, there we go now. Hello and welcome.
All right, thank you. Is this working now? Thank you. Yes? No? Thanks. All right, so while I'm waiting for questions to appear on the Slido, do we have Andres here?
I hope you can hear me. Hi.
Oh, okay, so I can hear you. I can't yet see you. Oh, there you go.
Okay. Yeah,
All
hi.
right.
So I'm sorry I could not be with you, but COVID got me the last week. I'm still actually positive, really positive person the last 8 days. Yeah, so I hope I can get some sentences out without having to cough too much. Yeah.
Okay, well, I have a question while we're seeing what the audience has to say, which is, I'm curious how robust to different experiments the clusters are. Like, as you discover clusters of symptoms and understand their root cause, does that become background knowledge for the future? And is there a way for the system, which is, by the way, gorgeous, it makes me want to do post-silicon validation, is there some way to keep that knowledge in the system for newcomers?
Yeah, well, it depends on the chip actually. So there are some issues which are like common for all of the chips, but some aren't. One of the main problems in the industry is that they do not share that much data. So it's really hard to find some type of benchmark data. That's actually one of the reasons why Advantes generated this synthetic data set for us. So yes, you can use some, but not all of the new things you find out.
This is one of the things that really makes testing hard, isn't it?
Yeah, for sure, definitely.
So I have another question, is that, we have this really high dimensional system, and you guys are using UMAP, which I think, has a lot of tuning that goes into it. So how did you guys decide what the parameters would be in your system?
Well, yeah, that's really a difficult part. They also wanted us to, one of the requirements was to have it as easy as possible regarding the hyperparameters. So we can actually put them on. They are there like expert mode, and then you would have all of these there. So we just did a little bit of trial and error with most of our data sets, and that's how we approached it. Yeah, and just iterate over it. If it's not having any clear divisions, any nice clusters which we could find, then we did it like that.
All right. Thank you. That's very useful for me as a designer. Do we have any other questions from the audience? All right, one more.
Thank you. Hi for the nice presentation again. And did you apply the system or thought about in a different domain that is not like a post-semiconductor validation, but it could be like, I don't know, automotive error tracking after production or something like that, or some different area, because especially the cluster finding thing where you have like one symptom that might cause different sorts of problems might be interesting.
Yes, I think that the main problem would also be something just like for me now, I got COVID, and we can as well say, okay, you have similar symptoms that refer to different illnesses as well. So I just didn't have the time to go really in depth with the different databases, or some nice data sets would be really significant for us. So no, I have not tried that in depth, but that's something we definitely want to do. Yeah.
Okay, thank you.
Thank you.
All right, thank you so much. I think we're at the end of this session. Thank you so much for being a great audience. Thanks for all of our speakers. We hope Anders gets very well very soon. So,
for sure, thank you very much.
And just one more reminder that there's a survey on the TestVis website. So if you're not coming back for the second session, please do take it and give us some feedback.